Tonight, we're going to explore something that has been quietly reshaping how scientists think about the fate of everything that exists. The universe is not just expanding. It is accelerating outward, driven by a force no one fully understands. And the number that captures that force is 73 kilometers per second per megaparsec, a number that should not be as frightening as it turns out to be. Because here's the thing most people don't realize, that acceleration is not slowing down, it is speeding up, and everything we know and everything we will ever know is slowly being pushed beyond the reach of any future observer. By the end of tonight, you're going to understand why the universe's expansion is accelerating rather than coasting to a halt, and what the ultimate fate of every galaxy, every star, and every atom implies for the question of why anything exists at all. Before we dive in, if you love exploring the deep mysteries of the universe as much as we do, take a moment to like the video and subscribe. It's a small thing, but it helps this channel grow and reach more curious souls like you. Now, let's begin. The number at the center of all of this is 68%. That is the fraction of everything that exists, the total energy budget of the universe, that is made of something no one can see, touch, or detect directly. Not matter, not light, not atoms or stars, or the dark matter that holds galaxies together. Something else. Something that fills every cubic centimeter of empty space with a faint but relentless push. And that push is winning. It has been winning for about 5 billion years now. And the harder you look at that number, 68%, the stranger and more unsettling the picture becomes. Let's start with what the universe looked like before anyone knew this was happening. In 1929, Edwin Hubble confirmed that the recessional velocity of a galaxy increases with its distance from Earth, a behavior that became known as Hubble's law. Working at the Mount Wilson Observatory in California, Hubble had gathered evidence showing that distant galaxies were moving away from us, and the farther they were, the faster they receded. This was not a small refinement to what astronomers already knew. That single observation overturned centuries of belief in a static, unchanging universe and laid the groundwork for modern cosmology. Before Hubble's paper landed in 1929, the prevailing view was that the Milky Way was essentially all there was. A single island of stars adrift in otherwise empty and motionless space. What Hubble showed was that the universe was not only larger than anyone had imagined, but that it was actively growing. Every galaxy beyond our local neighborhood was moving away from every other galaxy, not because the galaxies themselves were flying through space, but because space itself was stretching. The fabric underneath everything was expanding like the surface of a balloon being slowly inflated, and every point on that surface was moving away from every other point simultaneously. Think about what that actually means for a moment. There is no center to the expansion. There is no edge rushing outward into emptiness. Every observer in every galaxy sees the same thing. All other galaxies receding, the more distant ones receding faster, because there is more expanding space between them. It is one of the strangest things physics has ever asked us to accept, and yet the evidence for it is written in the light from 10,000 galaxies, each one carrying in its spectrum the telltale redshift, the stretching of its light toward longer wavelengths that comes from being carried away on a tide of expanding space. So by 1929, the universe was understood to be expanding. The reasonable question that followed was, how fast is it expanding, and will it slow down? Gravity, after all, acts on everything. Every galaxy pulls on every other galaxy. Every cluster of matter tugs against the outward flow. The expectation, held by almost every cosmologist for most of the 20th century, was that the expansion would decelerate. The early universe had been launched outward by the Big Bang with tremendous energy, but gravity would act as a brake. The only real question was whether there was enough matter in the universe to reverse the expansion entirely, pulling everything back toward a final collapse called the Big Crunch, or whether the expansion would simply slow and coast toward a cold, thin, but permanent spread across infinite space. Either way, deceleration was the assumption. It was built into every model. It was what the physics predicted. It was wrong. In 1998, two teams who had set out to measure the expected deceleration in the expansion of the universe instead made an astounding discovery. The universe had been accelerating in its expansion for the last few billion years. The way they found this is worth understanding in detail, because the method is as remarkable as the finding. The two teams, working independently and in competition with each other, were looking at a specific kind of exploding star called a Type Ia supernova. A Type Ia supernova is thought to occur when a white dwarf star gains enough additional mass to pass above a critical threshold, either by pulling material from a companion star or, as many researchers now think plays an equally important role, through the eventual merger of two white dwarfs. The exact mix of these two channels is still an active area of research. Since all Type Ia supernovae are believed to occur in essentially the same way, they form a standard candle whose intrinsic luminosity can be assumed to be approximately the same in all cases. That last phrase, standard candle, is the key. Because these explosions are triggered when a white dwarf approaches a critical mass. They produce a fairly consistent peak brightness, and astronomers use that consistency as a standard candle. By comparing how bright a supernova appears from Earth against how bright it actually is, they can calculate its distance. It is an elegant technique. You know how bright the explosion should be. You measure how bright it actually appears from here. The difference tells you the distance. Then you compare that distance to the redshift of the galaxy hosting the supernova, which tells you how fast that galaxy is receding. Do this for enough supernova across a wide range of distances, and you build up a map of how the expansion rate has changed over billions of years of cosmic history. You are, in effect, reading the autobiography of the universe's expansion from the light of ancient stellar explosions. Two independent collaborations, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt, conducted surveys to discover and measure Type Ia supernova at high redshifts. Adam Rees led the analysis of the High Z team's data and was first author on its landmark 1998 paper. By 1998, the Supernova Cosmology Project had gathered 42 high redshift supernova, while the High Z team's initial published sample included 16 high redshift supernova combined with 34 nearby ones for calibration. And when they analyzed the data, both teams found the same thing, independently, using different instruments and different methods. The distant supernovae were fainter than expected, given how redshifted their light was. This implied that not only was the universe expanding, but the expansion was accelerating, fainter than expected. It sounds like a small thing, a technical footnote. But think through what it means. If the distant supernovae were fainter than their redshifts would suggest, There was only one explanation. They were farther away than the redshift alone would predict. And if they were farther away than expected, the universe had expanded more than expected during the time the light was traveling to us. It had expanded more, not less, than a decelerating universe would produce. The universe was not slowing down. It was speeding up. The supernova observations created the largest cosmological bombshell since Edwin Hubble's 1929 paper that convinced the world of the universe's expansion. The discovery was named by Science magazine in 1998 as the breakthrough of the year. In 2011, Perlmutter was awarded the Nobel Prize in Physics for this work, alongside Adam Rees and Brian Schmidt from the High Z team. But the Nobel Prize and the discovery headlines are almost beside the point right now. What matters is the thing underneath. What could possibly be pushing the universe apart? What force overcomes gravity at cosmic scales, not just locally, but everywhere, in every direction simultaneously, growing stronger as the universe grows larger? The teams had named the culprit. They had called it dark energy. But naming it is not the same as understanding it. And here is where the story gets stranger and considerably harder. Let's talk about what dark energy actually is. Or more precisely, let's talk about the honest state of what we know, which is considerably less comfortable than the textbook summary suggests. You've probably heard that dark energy is the energy of empty space. That is the simplest version, and it is not wrong, but it is missing almost everything important. The textbook answer is that space itself has some inherent energy density, a kind of baseline hum of energy woven into the vacuum. As the universe expands, more space comes into existence, and that space carries energy with it, driving further expansion, which creates more space, which carries more energy. The expansion feeds itself. It is self-reinforcing. That picture is almost entirely correct as far as it goes, but the moment you ask why the vacuum has the energy density it has, the picture collapses into one of the deepest unsolved problems in all of physics. The modern understanding of the vacuum, based on quantum field theory, is that vacuum energy arises naturally from the totality of quantum fluctuations, meaning virtual particle-antiparticle pairs that come into existence and then annihilate each other shortly thereafter in empty space. This is not speculation. Quantum field theory is the most precisely tested framework in the history of physics. Its predictions for the behavior of electrons and photons have been confirmed to 1 part in a billion. The vacuum is not empty in this framework. It seethes with activity, with particles flickering in and out of existence on timescales so short they are almost below the concept of time itself. The problem is what quantum field theory predicts for how much energy all of this flickering produces. Estimates vary by source and by the cutoff scale assumed, but the observed density of the cosmological vacuum energy is roughly 10 to the power of -8 to -10 ergs per cubic centimeter, while values predicted from quantum field theory run from around 10 to the power of 110 up to 10 to the power of 113 ergs per cubic centimeter. This discrepancy of 10 to the 120 was known even before the discovery of the far weaker dark energy. Let that number sit for a moment. 10 to the 120. That is a 1 followed by 120 zeros. That is the gap between what quantum mechanics predicts for the energy of the vacuum and what the actual vacuum appears to contain. The most natural estimate of vacuum energy is 50 to 120 orders of magnitude larger than what dark energy actually is. This profound discrepancy between theory and observation is the cosmological constant problem. It is widely considered the worst prediction in the history of physics. Not slightly wrong, not off by a factor of 2 or 10 or 1,000. Off by a factor that makes the ratio of a proton to the observable universe look like a rounding error. The universe contains an amount of vacuum energy that is incomprehensibly smaller than the amount quantum field theory says it should contain, and no one knows why. One reasonable response to this discrepancy would be to say, perhaps the vacuum has no energy at all, and what we are observing is something else. Perhaps dark energy is not vacuum energy, but a different kind of energy field, one that changes over time, one that has a specific value today because of where we happen to be in cosmic history. Some models replace the cosmological constant with a dynamical field, sometimes called quintessence, where dark energy evolves over time rather than remaining constant. Quintessence is an appealing idea. It sidesteps the worst of the cosmological constant problem by essentially saying the vacuum energy is zero, and what we observe is something else layered on top. The simplest possibility involves a scalar field, rolling slowly in a potential sometimes known as quintessence, the same kind of source typically invoked in models of inflation in the very early universe. But quintessence has its own problems. It requires fine-tuning of a different kind. The field must be extraordinarily light, with properties calibrated to produce the right amount of acceleration at precisely this moment in cosmic history. It must also not clump the way matter does, otherwise its effects would not be uniform across the sky, and observations show that they are. Every test we have run has been consistent with the simplest model, the plain cosmological constant, the fixed vacuum energy density, the number that does not change. And yet that number's value remains, to the deepest understanding of physics, completely unexplained. The nature of this dark energy remains a mystery. That sentence, taken from a NASA summary, is not a placeholder for an eventual answer. It is the honest current state of knowledge. The physicists who discovered the acceleration of the universe have spent decades since trying to understand what is causing it, and the answer has not come. The mathematical description works. The prediction of the Hubble constant, the clustering of galaxies, the temperature fluctuations in the cosmic microwave background, all of it lines up when you include a cosmological constant of the right size. But why it has that size, why it is not zero, why it is not enormous, why it is precisely in the range that allows galaxies and stars and planets and life to form before the universe flies apart, remains genuinely, deeply unknown. Stop here for a moment and take stock of where we are. The universe is made mostly of something we cannot explain. 68% of everything, by energy content, is dark energy, a substance or property of space whose origin and nature are not understood by the most sophisticated physical theories ever devised. Another 27% is dark matter, which we will come back to. That leaves roughly 5% for everything you have ever seen or touched or detected. Atoms, molecules, light, all the visible matter of all the stars and galaxies and clouds of gas that fill the night sky. 5%. In the universe's own accounting, ordinary matter, the stuff of chemistry and biology, and every instrument ever built to study the cosmos is a trace ingredient. A minor footnote in a budget dominated by things that do not show up in any telescope, that interact with nothing except through the pull and push of gravity. And the dark energy is not sitting still. It is working. Astronomers have strengthened the evidence that the early universe was decelerating, but that it gave way to acceleration by around 4 to 5 billion years ago. That transition from a decelerating universe to an accelerating one is the pivot point in the story of everything that will ever exist. For most of cosmic history, gravity was dominant. Matter was denser, galaxies were closer together. The gravitational pull of the universe on itself was stronger than the outward push of dark energy. The universe expanded, but it expanded less quickly over time as gravity worked to pull things back. Structures could form, matter could clump, galaxies could merge and grow, stars could ignite and burn and die. Life had time to emerge. But roughly 5 billion years ago, the universe had expanded enough that matter became dilute enough, and dark energy persistent enough that the balance tipped. Because here is the crucial difference between gravity and dark energy. As space expands, gravity weakens. Matter spreads out. The gravitational pull between distant things decreases as the distance increases. Dark energy, on the other hand, does not dilute. If it is a property of space itself, then as new space comes into existence, it brings its vacuum energy with it. The energy density stays constant even as the universe grows. So gravity was always going to lose this contest. It was only a matter of when, 5 billion years ago, when it arrived. And since then, the universe has been accelerating outward, with dark energy as the driver, and with every passing year the galaxies pull a little farther apart. The acceleration compounds, and the question of what lies at the end of this process becomes increasingly unavoidable. That question will take us somewhere genuinely confronting. But before we get there, we need to understand what 68% of the universe being dark energy actually means in physical, measurable terms. Because the number is not abstract. It shows up in measurements. It shapes the universe in ways we can observe and calculate. And those observations, taken together, build a picture that is both more precise and more strange than almost any popular account of dark energy conveys. Let's talk about the evidence and how the case for dark energy has been built layer by layer by entirely independent methods that all point to the same unsettling conclusion. The supernova results of 1998 were the first evidence. They were compelling, but not definitive. A single method, even a beautiful one, leaves room for doubt. Perhaps the distant supernovae were fainter, not because the universe was accelerating, but because intergalactic dust was absorbing some of their light. Perhaps Type Ia supernovae were not quite as uniform in the distant universe as they are nearby, and the evolutionary differences were biasing the results. The two teams had considered and addressed these objections, but the community rightly demanded confirmation from independent methods. The first independent confirmation came from the cosmic microwave background, the faint thermal afterglow of the Big Bang that fills the entire sky at a temperature of about 2.7 degrees above absolute zero. The Wilkinson Microwave Anisotropy Probe, known as WMAP, launched in 2001 and spent 9 years mapping the tiny temperature fluctuations in this background radiation. Those fluctuations, which are the imprints of sound waves in the early universe, carry information about the total energy content of the cosmos. A flat universe, one with the critical density of matter and energy needed to balance the expansion exactly, produces fluctuations of a specific angular size in the sky. Subsequent observations, including more detailed studies of supernovae and independent evidence from the cosmic microwave background and large-scale structure and clusters of galaxies, confirmed and firmly established the remarkable finding of cosmic acceleration. WMAP found that the universe is flat to within the precision of measurement, and a flat universe with only 5% ordinary matter and 27% dark matter has the wrong total energy density. The numbers only add up if about 68% of the universe is something like dark energy. Then came the large-scale structure of galaxies. When galaxies form and cluster together, the distribution of those clusters across the sky carries the imprint of the early universe's conditions. Those conditions included a specific length scale called the baryon acoustic oscillation scale, which is essentially the distance sound waves traveled in the first 380,000 years after the Big Bang, before the universe cooled enough for atoms to form and the waves to freeze in place. That frozen length scale, about 500 million light-years, acts as a cosmic ruler. By measuring how galaxy clustering statistics change with distance and redshift, astronomers can track how the expansion of the universe has changed over time. And again, the answer comes back. The universe accelerated its expansion starting several billion years ago, driven by something with properties consistent with a cosmological constant. Each of these three methods, supernovae, the cosmic microwave background, and baryon acoustic oscillations, has been cross-checked and refined over 2 decades. Precise measurements by the Planck satellite reveal the contributions of dark energy to the overall energy density of the universe, consistent with a cosmological constant. The European Space Agency's Planck mission, which operated from 2009 to 2013, produced the most precise map of the cosmic microwave background ever made, with temperature fluctuations resolved to 1 part in 100,000 across the full sky. Its 2018 final mission results pinned the dark energy fraction at approximately 68.5 to 69%, and the matter fraction at approximately 31.5%, slightly refined from the widely popularized 68.3%, 31.7% figures of Planck's earlier 2013 release. With the flatness of the universe measured to a precision that rules out significant curvature. Every independent measurement agrees to within the margin of experimental error. This is what a scientific consensus looks like when it is earned rather than assumed. It is not one team finding one result. It is multiple methods, multiple instruments, multiple teams on multiple continents, all converging on the same extraordinary conclusion. The universe is mostly dark energy. The expansion is accelerating. The acceleration has been running for 5 billion years and is going to keep running, as far as anyone can tell, indefinitely. And here is where the picture turns from strange to genuinely confronting. If the acceleration continues, and there is currently no observational evidence that it will stop, the universe will not end with a collapse. It will not end with a crunch. It will end with something more like a dissolution. The galaxies that are already gravitationally bound to each other, our own Milky Way and its companions in the local group, will remain together. Gravity holds them close enough that dark energy's push is too weak to separate them. But the galaxies beyond our local neighborhood are already being carried away by the expansion at speeds that are, in effective terms, faster than light. Not because anything is moving through space faster than light, but because the space between us and those distant galaxies is stretching so rapidly that light emitted from those galaxies today will never reach us. There is a boundary in space called the cosmological event horizon, and it is defined by exactly that. The distance beyond which light emitted today will never arrive here, because the expansion will carry the source away faster than the light can travel. Everything beyond that horizon is, in the most practical sense, permanently beyond reach, not just far away, gone, and the horizon is shrinking. Not in absolute terms, not yet, but in terms of what it contains. As the acceleration continues, more and more galaxies are carried beyond it. Their last photons reach us, and then nothing more follows. From our perspective, they gradually redshift to invisibility, their light stretching toward infinitely long wavelengths, their clocks appearing to slow and freeze at the horizon's edge. Then silence. One by one, the universe erases its own contents from the observable sky. This process takes an almost incomprehensibly long time. Not billions of years, trillions, quadrillions. The timescales of this erasure dwarf the current age of the universe the way the age of the universe dwarfs a human heartbeat. But the direction is what matters. It is not toward more complexity, more structure, more richness. It is toward isolation. It is toward a universe in which the Milky Way and its nearest companions float alone in an expanding void, with no other galaxies visible, with no way to detect or measure the expansion that caused the isolation, with no record of what came before. Consider what that means for any future civilization, however advanced, that might exist in the Milky Way 1 trillion years from now. They will look out at the night sky and see only their own galactic neighborhood. The evidence for dark energy will be gone. The expanding universe will be invisible. Once researchers understood that the universe is expanding faster now than it did when it was young, they realized it had to be several billion years older than previously thought. The reasoning that let us discover dark energy at all, the comparison of nearby and distant supernovae, the mapping of the cosmic microwave background, the measurement of galaxy clustering at different epochs, all of these rely on the ability to see distant galaxies. Remove them from the observable sky, and a civilization of the future, however intelligent, would have no observational basis to suspect that dark energy exists. They would inherit a universe that looks, for all available evidence, static and alone. Knowledge is not automatically inherited. That is perhaps one of the quieter implications woven into what we are exploring tonight. The ability to understand the universe depends on what the universe allows you to see. And what the universe allows you to see is changing. This brings us back always to the 68%. Not just as a number, but as a force. As something that is actively reshaping what the universe will eventually become, and what any future mind will eventually be able to know about it. We will go deeper into that reshaping in the sections ahead. But for now, let's sit with the foundation. The universe is accelerating. The evidence is overwhelming and independent. The cause is something called dark energy, which is consistent with vacuum energy, which is utterly unexplained by the deepest physical theories we have. And the consequences of that acceleration, run forward in time, are not gentle. The dark energy story does not exist in isolation. To understand why 68% of the universe being dark energy is as strange as it is, you need to understand what the other 32% is made of, and what the picture of the universe looks like when you hold all of it together. Because the 68% is the dominant mystery, but it sits alongside another mystery that is only slightly less deep. And the two together paint a picture of a cosmos in which ordinary matter, the kind that makes everything you can see and touch and build with, is essentially an afterthought. Let's talk about dark matter. The case for dark matter began in 1933, when a Swiss-American astronomer named Fritz Zwicky was working with the Coma Cluster, a dense knot of about 1,000 galaxies, roughly 320 million light-years from Earth. Zwicky estimated the velocity dispersion of the cluster, meaning how fast the individual galaxies within it were moving relative to each other, and found something that made no sense. The cluster was spinning so fast that it ought to burst apart. The galaxies were moving far too quickly to be held together by the gravity of the visible matter he could account for. By his calculation, the cluster would need to contain hundreds of times more mass than the visible stars and gas could provide. He concluded that there must be something invisible holding it together, something he called dunkel Materie, dark matter. The concept did not catch on. It was, as Netta Barkal of Princeton University has described, too outrageous to believe for almost 4 decades. The overwhelming majority of astronomers and physicists dismissed it. It sat on the edges of cosmology for 30 years, an anomaly no one was sure what to do with. Then, in the 1970s, Vera Rubin changed everything. Rubin, working with her collaborator Kent Ford, was studying the rotation curves of spiral galaxies, in particular the Andromeda Galaxy and dozens of others. A rotation curve simply plots how fast stars are orbiting the center of their galaxy as a function of how far they are from that center. The physics of how this should look was not mysterious. If a galaxy's mass is concentrated near its center, where the light is brightest and the stars are most densely packed, then stars at the outer edge of the galaxy should orbit more slowly than stars near the center, for the same reason that the outer planets of the solar system orbit the sun more slowly than the inner ones. Gravity weakens with distance. You would expect the rotation curve to fall off steeply as you move outward from the galactic core. What Rubin found was that the curve was flat. The stars at the outer edge of Andromeda were orbiting at nearly the same speed as the stars near the center. When Rubin plotted the rotational velocity of stars in M31 as a function of their distance from the galaxy's center, the curve trailed off in a nearly flat line. The orbital velocities of stars far from the center did not decrease as expected. Instead of slowing down, they were moving at speeds that simply could not be explained by the visible matter in the galaxy. There was far more mass exerting a gravitational pull than the stars and gas could account for. Rubin's calculations showed that galaxies must contain at least 5 to 10 times more mass than can be observed directly based on the light emitted by ordinary matter. Rubin spent the 1970s accumulating galaxy after galaxy, rotation curve after rotation curve. Every one of them told the same story. Practically all spiral galaxies have extended flat rotation curves. The concept of dark matter halos surrounding galaxies was confirmed with a high confidence. There was an invisible sphere of matter surrounding every galaxy she studied, a halo of something that neither emitted nor absorbed light, but that exerted an unmistakable gravitational influence on everything around it. This was not Zwicky's cluster anomaly, a strange measurement that could be attributed to systematic error. This was a universal feature. Galaxy after galaxy, the flat rotation curve appeared. The only explanation was dark matter. Today, dark matter accounts for approximately 27% of the universe's total mass energy content. It is distributed in halos around galaxies and clusters of galaxies. It does not interact with light. It does not interact with ordinary matter through any force other than gravity. Despite decades of experiments using underground detectors in abandoned mines, particle accelerators like the Large Hadron Collider at CERN, and satellite observatories scanning the gamma-ray sky, no direct detection of a dark matter particle has been confirmed. We know it is there because of what gravity does. We have no idea what it actually is. So here is the full inventory. 5% ordinary matter, 27% dark matter, 68% dark energy. The universe is 95% composed of things we cannot directly detect and do not understand. The fraction of everything that is actually familiar to us, the stuff that makes up planets and people and the light of stars, fits comfortably within a 5% share of cosmic reality. The rest is darkness of two different, equally baffling kinds. Take stock of where we are, because this context matters for what comes next. Dark energy pushes outward. Dark matter pulls inward, helping gravity hold structures together. Ordinary matter falls into the wells that dark matter creates and ignites into stars and galaxies. The universe, as it stands, is a delicate negotiation between these three components. And for most of its 13.8 billion year history, that negotiation has produced structure. Galaxies, clusters, superclusters, the vast cosmic web of filaments and voids that looks, at large scales, like a three-dimensional foam of matter threaded through by emptiness. But the negotiation is tilting. It has been tilting for 5 billion years, since the moment dark energy's fraction of the total energy budget crossed above dark matter's fraction and began to accelerate the expansion. And as the tilting continues, the large-scale structure of the universe is slowly being unwritten. Here is where things get harder. And here is where the numbers acquire a genuinely confronting quality. Let's talk about the Hubble tension, because it is not merely a technical dispute between two measurement methods. It is a crack in the standard model of cosmology, and the crack has been widening for over a decade. The Hubble constant is the rate at which the universe is currently expanding. It is measured in kilometers per second per megaparsec, meaning for every megaparsec of distance between 2 points in the universe, those 2 points are moving apart at a speed equal to the Hubble constant. The problem is that two independent ways of measuring it give two different answers, and those answers disagree at a level that is almost certainly not a measurement error. The first method measures the Hubble constant from the early universe, using the cosmic microwave background. The Planck satellite, which mapped the CMB with extraordinary precision, gives a value of about 67 kilometers per second per megaparsec. The second method measures it from the local universe, using the distance ladder built from Cepheid variable stars and Type Ia supernovae. Adam Rees and the SHZUES team, using the Hubble Space Telescope and later confirmed by the James Webb Space Telescope, get a value of about 73 kilometers per second per megaparsec. These two numbers differ by roughly 9%. That sounds small. It is not. In the language of statistics, where disagreements are measured in units of standard deviation, the discrepancy between these measurements has reached 5 sigma, meaning the probability of the disagreement being a random fluke is 1 in 3.5 million. A 5 sigma discrepancy is what physicists call a discovery. In particle physics, 5 sigma is the threshold for announcing a new particle. Here, it is announcing something much more unsettling, that the standard model of cosmology, the lambda CDM model that has successfully described the large-scale structure of the universe, the expansion history, the distribution of galaxies, and the fluctuations in the cosmic microwave background, may be incomplete or wrong. The tension may indicate the presence of unknown systematic errors, or it may point toward new physics beyond the standard cosmological model. Some proposals suggest that a distinct form of dark energy existed briefly in the early universe, a so-called early dark energy that would have accelerated the early expansion in ways that alter the predictions of the CMB-based measurements. Others suggest that dark energy is not a constant, but a field that changes over time, or that dark energy interacts with dark matter, or that gravity itself behaves differently at cosmic scales than the standard model assumes. In 2024, data from the Dark Energy Spectroscopic Instrument, known as DESI, provided evidence hinting that dark energy may not be constant. The results suggested a dynamic form of dark energy that may be evolving over time. This discovery, if confirmed, would not resolve the numerical disagreement between the two Hubble constant measurements, but it would fundamentally change what dark energy is understood to be. A constant vacuum energy is one thing. A field that is changing, that has a past and a future that are different from its present, is something else entirely. Something with dynamics. Something that might have been different in the early universe and might be different in the far future. The honest assessment here is that the Hubble tension remains the most significant puzzle in cosmology as of now, and there is currently no convincing solution. The standard model fits most of the data very well, but the crack between 67 and 73 kilometers per second per megaparsec is real. It has survived every attempt to explain it away, and the James Webb Space Telescope has verified the local measurements rather than reducing the gap. What the tension tells us, at minimum, is that our map of the universe is incomplete. The framework that has been the foundation of cosmology for 3 decades may need revision. And the nature of the revision, whether it is a modest adjustment to the properties of dark energy or something that overturns our basic understanding of how gravity works at large scales, is genuinely unknown. There is something important to sit with in that admission. The cosmological constant, that mysterious number representing the energy density of the vacuum, was first introduced by Albert Einstein in 1917 as an addition to his field equations of general relativity. Einstein introduced it to counterbalance the effect of gravity and achieve a static universe, which was then assumed. When Edwin Hubble showed in 1929 that the universe was expanding, Einstein is said to have called the cosmological constant the greatest blunder of his life, though this famous quote comes only from a second-hand account by physicist George Gamow, told after Einstein's death, and its accuracy has been questioned by historians of science, who have found no written record of Einstein using the phrase himself. What is well documented is that Einstein did drop the term from his equations once the expansion was confirmed. From the 1930s until the late 1990s, most physicists thought the cosmological constant to be zero. Then 1998 arrived, and the constant came back. And its return has proven to be far more strange than even the original blunder. A number so fine-tuned, so precisely calibrated between the prediction of quantum mechanics and the observations of cosmology, that it sits at a value that permits the universe to exist as we know it, and for which no physical theory provides an explanation. Why is the cosmological constant the value it is? There are three honest answers. The first is that we have not yet found the right theory. Perhaps a future unification of quantum mechanics and general relativity, a quantum theory of gravity that does not yet exist, will predict the value from first principles. String theory and loop quantum gravity are the two leading candidates for such a theory. Neither currently makes a successful prediction of the cosmological constant. Neither has been confirmed by experiment. The honest position is that this is an open problem, one of the deepest in all of physics, and the solution is not obviously at hand. The second answer is the anthropic argument, uncomfortable as it is for physicists who prefer their constants to be derivable from deeper principles. The cosmological constant might take different values in different regions of a much larger multiverse. In most of those regions, the value is either so large that it tears everything apart before structure can form, or so negative that it causes collapse before stars can ignite. We happen to live in a region where the value is just small enough to allow galaxies, stars, and planets to form, because in any other region we would not exist to ask the question. This is not a prediction, it is an explanation of the last resort. Some physicists find it compelling, others find it deeply unsatisfying, because it provides no actual mechanism and makes no testable predictions. The third answer is that the question is wrong. Perhaps the cosmological constant is not a number that needs explaining in isolation, but an emergent property of something larger, something that will only become clear once the framework of physics has advanced well beyond where it is today. What is not disputed is the observation itself. The expansion is accelerating. The acceleration began 5 billion years ago. The cause is dark energy. Dark energy currently constitutes 68% of the total energy budget of the universe. And the acceleration is not gentle. It is not a small nudge. It is the dominant fact about the universe's future. Everything that happens from here, on timescales long enough to matter cosmologically, is downstream of that single 68%. Let's talk about the cosmological event horizon and what it means for what we can and cannot know. The event horizon in cosmology is defined by the accelerating expansion. It is the distance beyond which any signals sent today will never reach us, because the space between here and there is expanding so fast that even light cannot close the gap. The horizon is not a physical wall. There is nothing special about the matter on the other side. It is simply the edge of causal contact, the boundary beyond which the universe has, in a practical and permanent sense, stopped communicating with us. The current cosmological event horizon is roughly 16 billion light-years away. The observable universe, by contrast, extends to about 46 billion light-years in every direction, Because light that left very distant sources shortly after the Big Bang has been traveling toward us for 13.8 billion years, even as those sources have been carried much farther away by the expansion. But the difference between the observable universe and the event horizon is crucial. The observable universe tells us what we can currently see, the history written in light that has already arrived. The event horizon tells us what will ever influence us, what we can ever receive a signal from. And everything beyond the event horizon is forever beyond the horizon. As the acceleration continues, the event horizon does not shrink in light years, but the number of galaxies within it does. Galaxies that are currently close to the edge of the horizon are being carried away. Their light is already traveling toward us, but arriving with a longer and longer wavelength as it climbs out of the expanding space. At some point, the last photon from a given galaxy arrives. The galaxy disappears from our sky, not violently, but gradually, fading to longer and longer wavelengths until it redshifts into silence. The sky does not go dark all at once. It empties over an incomprehensible span of time, one galaxy at a time, each one reaching its final apparent brightness and then slowly dissolving. The galaxies of the Virgo cluster, the massive collection of galaxies about 50 million light-years away that anchors our local supercluster, are already on a path that will eventually carry them beyond effective contact. The timescales for this are vast, many billions of years, but the direction is fixed. The Virgo cluster will one day be as unreachable, as invisible to any future observer in our galaxy, as a galaxy already beyond the event horizon is today. What remains, most likely, is the local group, the Milky Way, the Andromeda Galaxy, the Magellanic Clouds, and a scattering of smaller satellite galaxies. A 2025 reanalysis, using updated Hubble and Gaia data, found that the long-assumed collision and merger between the Milky Way and Andromeda, sometimes called Milkomeda in popular accounts, is far less certain than once thought. Accounting for measurement uncertainty and the gravitational pull of nearby satellite galaxies, researchers found only about a 50% chance the two galaxies merge within the next 10 billion years, with less than a 2% chance of the head-on collision in roughly 4 to 5 billion years that was previously treated as near inevitable. And Milkomeda will float alone in a universe that has emptied around it, with no visible neighbors, no other galaxies, no evidence in the sky of the vast cosmic web that once stretched in every direction. This is not a big rip, which would require a different form of dark energy. The Big Rip is a hypothetical cosmological scenario in which matter of the universe, from stars and galaxies to atoms and subatomic particles, is progressively torn apart by a runaway expansion that accelerates without limit, eventually pulling apart even the most tightly bound structures. This would require what physicists call phantom energy, a form of dark energy with a specific property. Its density increases rather than remaining constant as the universe expands, making the acceleration compound into a true runaway, a divergence in finite time. Current observations are consistent with a cosmological constant, meaning a dark energy whose density stays fixed and does not increase. But the possibility of phantom energy has not been completely ruled out, and the recent DESI results, hinting at dynamical dark energy, have kept the question alive. For now, the standard expectation is the slower scenario. Not the rip, but the emptying. Not a violent conclusion, but a quiet erosion. Dark energy wins not by tearing everything apart, but by carrying everything out of sight. The universe's fate, under the most likely scenario, is isolation. A magnificent, continent-spanning civilization in some future galaxy that is not our own will eventually find itself utterly alone, surrounded by void, with no evidence that any other galaxy was ever there. There is something in that image that is worth dwelling on before we move further. It goes back, always, to the 68%. That is what dark energy is, at the observational level. A fraction. An accounting entry in the universe's balance sheet. A number that emerged from measurements of faint supernovae by teams of astronomers who expected to confirm deceleration and found instead the opposite. A number that has been confirmed by the cosmic microwave background, by baryon acoustic oscillations, by the distribution of galaxy clusters across the sky, by every independent test that cosmologists have been able to devise. And yet, no one knows what it is. No theory predicts it correctly. The only model that fits the observations is one that includes a parameter, the cosmological constant, whose value is unexplained. The model works. The explanation does not exist. That tension between the remarkable predictive success of the cosmological model and the complete absence of any understanding of the model's central ingredient is one of the strangest and most productive tensions in the history of science. It is also not going away. The Hubble tension, the DESI hints at evolving dark energy, the persistent failure of any particle physics experiment to identify dark matter, the enormous gap between the quantum prediction of vacuum energy and the observed cosmological constant, all of these are active, unresolved problems. Not dead ends. Not anomalies that will dissolve with better measurement. The better the measurements get, the more precise the disagreements become. We are at a moment in cosmological history where the data are excellent and the explanations are inadequate. The universe is telling us something. The accelerating expansion is real. 68% is real. What it points to, beneath the mathematics and the measurements, is a cosmos that is more complicated, more surprising, and more willing to contradict our expectations than any model we have yet built. That is not a failure of science. It is science doing what it does best, encountering the world as it actually is, rather than as we assumed it would be. What the DESI instrument has been doing, out in the night sky above Kitt Peak in Arizona, is essentially taking the pulse of dark energy. It is the dark energy spectroscopic instrument, and over its first 3 years of operation, it has mapped the three-dimensional positions of tens of millions of galaxies across vast stretches of cosmic history, using the baryon acoustic oscillation scale as a ruler to trace how the universe has been expanding at different epochs. The numbers that came out of that mapping have unsettled the standard picture in a way that the cosmological community is still working through. Let's talk about what DESI found and why it matters so much. The standard model of cosmology, known as lambda CDM, lambda for the cosmological constant and CDM for cold dark matter, treats dark energy as a fixed property of space. One number. One value that never changes. If the cosmological constant is truly constant, then the equation of state parameter that describes dark energy, the ratio of its pressure to its energy density, should sit precisely at -1, not -0.9. Not -1.1, exactly -1. That is the mathematical signature of a true cosmological constant, a vacuum energy that neither grows nor shrinks as the universe expands. That was the same 10 billion years ago as it is today. In April 2024, DESI released the results from its first year of observations, and those results showed a slight but statistically notable preference for a dark energy equation of state that is not exactly -1. The preference was for a model in which dark energy has been changing over cosmic time, not dramatically, not wildly, but enough at the measured level to push against the assumption of a fixed cosmological constant. That first result was interesting, but not conclusive. The statistical significance was at a level that warranted attention without demanding a verdict. And so the DESI team collected more data. In March 2025, the collaboration released the analysis from its first 3 years of observations. The evidence for a time-evolving dark energy equation of state had increased since the first data release. The preference for evolving dark energy over a cosmological constant reached as high as 4.2 sigma in DESI's second data release, when combined with the cosmic microwave background and one particular Type Ia supernova catalogue, DES Year 5. Though the figure drops to about 2.8, 3.8 sigma with other supernova datasets, a dependency that is itself still debated among cosmologists. That is not yet the 5 sigma threshold that physicists conventionally call a discovery. But 4.2 sigma in statistics means the probability of this being a random fluctuation is roughly 1 in 60,000. It is a signal, and a persistent one, and it has been confirmed by the extra tests run to ensure the result was not being driven by some unknown effect in any of the data. What does evolving dark energy actually mean? It means dark energy is not simply a property of space that is the same everywhere and always. It means dark energy has dynamics. It has a past that may be different from its present, and a future that may be different from either. If the dark energy density was different in the early universe than it is today, then our calculation of the universe's expansion history needs revision. It affects the age of the universe, the predicted distribution of galaxy clusters, the calibration of distances across cosmic time. It potentially changes the answer to the Hubble tension. And if dark energy is evolving now, the question of where it is going, whether it is growing stronger or weakening, becomes the central question of observational cosmology. Here is where the picture both clarifies and deepens. There are 2 directions evolving dark energy could be heading. If its strength is declining over time, then the acceleration of the universe will eventually slow. Dark energy will fade. Gravity will reassert itself. The universe's future becomes less about isolation and more about a gradual winding down. Not a rip, not a crunch, but a long and quiet deceleration towards something more ambiguous. This possibility is sometimes called thawing dark energy, a field that starts frozen and slowly unfreezes, gradually dissipating its energy. The other direction is the one that generates the most concern in cosmological circles. If dark energy is strengthening over time, if its density increases as the universe expands rather than staying constant, then the future of everything changes drastically. This is the phantom energy scenario, the one that leads to the Big Rip. The DESI data, taken alone, hints that dark energy may have been stronger in the past and is weakening now, which actually points toward the thawing scenario rather than phantom energy. But the combination of different supernova datasets with the DESI measurements produces slightly different answers, and the consensus is not yet universal. Some combinations of data show a possible phantom crossing, meaning dark energy's equation of state parameter dipping below -1. The honest position on all of this is that the cosmological community has a 4.2 sigma hint of something new. Multiple independent instruments converging on a consistent time dependence for dark energy, coming from multiple measurement methods, and no agreement yet on what it means. The DESI results are not a discovery in the definitive sense. They are the leading edge of a possible discovery, and the next several years of data from DESI's ongoing survey, from the Euclid Space Telescope, from the Vera-C, Rubin Observatory's legacy survey of space and time will determine whether the hint solidifies into a confirmed detection of new physics. Stop here and take stock of what this means at a deeper level. If dark energy is a constant, then the cosmological constant problem is the central mystery. Why does the vacuum have the energy density it has, and not a value either zero or enormously larger? That mystery sits unanswered, but at least stable. The universe has always had this much dark energy. It will always have this much. The acceleration is a permanent, predictable feature of the universe's future. But if dark energy is evolving, the mystery changes shape. Now the question is not just what dark energy is, but what governs its evolution. What field is this? What is its potential energy landscape? What determined its value in the early universe, and what is driving its change now? A dynamical dark energy field with a changing equation of state has many more parameters than a simple cosmological constant. It has a past and it has a trajectory. And the trajectory carries implications for the very far future that a static constant does not. The fine-tuning problem sits underneath all of this, like a foundation made of fog. In 1987, physicist Steven Weinberg published a paper titled Anthropic Bound on the Cosmological Constant in Physical Review Letters. Weinberg was already a Nobel laureate, having helped establish the standard model of particle physics, and this paper has turned out to be one of the most provocative contributions to cosmological thinking since the discovery of the expanding universe. His argument was straightforward and deeply uncomfortable. If there exists a multiverse, a vast ensemble of regions of space, each with different values of the cosmological constant, then we should not expect to find ourselves in a region where the constant is exactly zero, or where it is enormous. A large positive cosmological constant would have caused the universe to expand so rapidly before structures could form that galaxies, stars, and planets would never have appeared. A negative cosmological constant would have caused rapid collapse. The cosmological constant cannot be negative and has to be very small if observers like us are to exist to ask questions about it. Weinberg made the prediction in 1987 that a non-zero cosmological constant would soon be discovered, because the anthropic bound was just a few orders of magnitude larger than the experimental constraints of the time. A little over a decade later, Perlmutter, Rees, and Schmidt found exactly that. Dark energy, sitting at precisely the value that allows structure formation and observers to exist. The prediction was confirmed. This is either the most important piece of reasoning about the cosmological constant or the most dangerous. It is important because it actually predicted the value years before it was measured. It is dangerous because it predicts very little else. It says nothing about which specific value the constant should have, only that it must fall within a range compatible with observers. It makes no predictions that can be tested at higher precision, and it requires as its foundation the existence of a multiverse, an ensemble of other regions of the cosmos with different physical constants, none of which can currently be detected or observed. Some physicists find this deeply troubling. If the value of the cosmological constant is explained not by any underlying mechanism, but simply by the requirement that we exist to observe it, then we have given up on a traditional goal of physics, the derivation of the constants of nature from deeper principles. The cosmological constant is not calculated, it is selected. Selected by the fact that it permits us to be here to wonder about it. Others find the argument inescapable. If the quantum prediction of vacuum energy is 10 to 120 times larger than the observed value, and if no known mechanism brings it down, then a selection effect in a multiverse may be the only framework in which the fine-tuning is not simply an unexplained miracle. Neither camp has a knockdown argument. Both positions face genuine difficulties, and the question is alive, contested, and unresolved. Let's walk forward in time now, not toward a theoretical debate, but toward what physics, run forward on its current trajectory, actually predicts for the universe's future. In their 1997 review in Reviews of Modern Physics, physicists Fred Adams and Gregory Laughlin mapped the deep future of the universe into a sequence of eras, each one dimmer than the last. The framework they developed has become the standard way of thinking about cosmic history's far future. And it is worth tracing in some detail, because it shows what dark energy's acceleration ultimately produces when you let it run. We are currently in what Adams and Laughlin called the stelliferous era, the age of starlight, the one we live in now. The universe is forming stars at a modest pace, burning through the hydrogen gas that gravity has compressed into ignition. Stars live and die, enriching the interstellar medium with heavier elements, cycling matter through the ongoing process of stellar evolution. The smallest stars, the cool red dwarfs that burn their hydrogens so slowly and so patiently, will keep shining for 100 trillion years, roughly 7,000 times the current age of the universe. Star formation itself will cease in about 1 to 100 trillion years, as the supply of gas needed will be exhausted. After that, the last shining stars will gutter out over a timescale that makes the entire current age of the universe look like the opening moments. But even before the last star dies, the isolation dark energy produces will be essentially complete. As the universe carries on expanding, we will no longer be able to observe galaxies outside our local group in a period measured in hundreds of millions of years, cosmologically speaking. The sky empties before the lights go out. Future civilizations in our galaxy will inherit a universe that appears, by all observable evidence, to be a single island of stars surrounded by void. After the stars die, the universe enters what Adams and Laughlin called the degenerate era. With the stars gone, what remains are their corpses: white dwarfs, neutron stars, brown dwarfs, and black holes. These objects slowly radiate their remaining thermal energy into the expanding void, growing progressively colder and dimmer. No new light is being generated. The universe is dim and cooling, populated by the slowly fading remnants of a stellar era that has passed. This phase lasts an extraordinarily long time, far longer than the stelliferous era that preceded it. If protons are themselves unstable, as some theories of particle physics predict, Even these dead remnants would slowly evaporate over something like 10 to 34th years or more. The atoms themselves dissolve. The degenerate remnants of stars lose their baryonic matter entirely, leaving only their gravitational influence and whatever dark matter halos still surround them. Then comes the black hole era. Eventually, black holes are the only large objects left. They grow by absorbing whatever matter remains in their vicinity, merging with each other over immense timescales. And then, through a process predicted by Stephen Hawking in 1974, even they begin to fade. Hawking radiation is one of the most remarkable predictions in theoretical physics. It arises from the interaction of quantum mechanics with the event horizons of black holes, which produces a faint thermal glow that slowly carries energy away from the black hole. The process is inconceivably slow. The most massive, supermassive black holes, those at the centers of large galaxies with masses billions of times that of the Sun, take approximately 10 to the 100th power years to evaporate completely. A Google years. That is a 1 followed by 100 zeros, a number so large that writing it in full would require a string of digits longer than the entire current observable universe is wide, if each digit were written at the scale of a hydrogen atom. After the last black hole evaporates, the universe enters the dark era. Only widely dispersed subatomic particles and extremely low-energy photons remain. The temperature approaches, but never quite reaches, absolute zero. The universe is in thermal equilibrium, with no energy available for any process, no gradient to drive any reaction, no work that can be done. This is heat death proper, a cosmos in thermal equilibrium, the final state of maximum entropy into which everything that ever existed, every star, every civilization, every thought and every signal has dissolved without remainder. The discovery in 1998 that the universe's expansion is accelerating, driven by dark energy, modifies this picture in one specific way. Without dark energy, a universe expanding at a constant or decelerating rate would allow in-principle access to more and more distant matter over time. With dark energy's acceleration, the observable universe is effectively shrinking in terms of new information. The heat-death scenario is not changed in its ultimate destination by dark energy, but the path is lonelier. Structures that form in the accelerating universe are more isolated. The material that could, in principle, have been incorporated into future stellar generations is carried away beyond the event horizon before it can be reached. The universe has less to work with in each future era than it would have had without the push. There is something in this sequence of eras that deserves more than a glance. It is not abstract. It is a timeline run from known physics across timescales that dwarf anything our intuition can compass. 100 trillion years for the last stars. 10 to the 34th years for proton decay, a Google years for the last black holes, and then the dark era, which has no end, which will last in principle forever, a universe of scattered particles drifting apart in an expanding void, each one carrying no information, no history, no trace of everything that came before. At each stage of this timeline, dark energy is present. It is the background condition against which everything else plays out. The acceleration it drives may not tear atoms apart if the cosmological constant holds constant. But it ensures that the universe that anything in the far future could observe is smaller emptier and more isolated than the universe we inhabit now. Every era of the universe's future is quieter and darker than the one before. Every era has access to less of the universe than the one before it. The direction of history is not toward richness, but toward dissolution. And underneath all of this, running through every era from the stelliferous to the dark, is the 68%, the dark energy fraction, the thing that fills space and pushes outward and cannot be directly detected and cannot be explained and refuses, despite every tool of physics trained upon it to yield a mechanism. It was there when the first stars ignited. It will be there when the last black hole dissolves into a faint whisper of Hawking radiation. It is the dominant fact about the universe's energy budget, and it is, in the deepest sense, a mystery that every generation of physicists for the foreseeable future will inherit unresolved. The question of whether we can ever know what dark energy is sits in the same uncomfortable space as the question of why it has the value it does. Not because the problem is intractable in principle, but because the tools we currently have are genuinely inadequate to the scale of the question. We can measure dark energy's effects with extraordinary precision. We cannot yet probe the underlying physics that produces it. We cannot reach inside the vacuum to sample its energy directly. We cannot step outside the universe to compare its cosmological constant to the distribution of constants in other possible universes, if such universes exist. We are in the position of creatures who can feel the effects of gravity pulling them toward the ground, who can measure and calculate those effects with extraordinary accuracy, but who cannot yet see the individual quanta of the gravitational field or unify the description of gravity with the quantum mechanics of the other forces. For gravity, that gap between measurement and mechanism has persisted for a century, despite the best efforts of theoretical physics. The gap in dark energy understanding may be similarly deep and similarly durable. That is not a comfortable place to rest, but it is an honest one. Right now, at this moment, two extraordinary pieces of hardware are watching the sky with the specific purpose of telling us more about what dark energy is and whether it is changing. One is already well into its work. The other is just beginning. Together, they represent the most ambitious observational effort ever aimed at the 68%. The Euclid Space Telescope, operated by the European Space Agency, launched on July 1, 2023, and began its cosmological survey on February 14, 2024. Its purpose is singular and large: to map the extragalactic sky over a period of 6 years, producing one of the most extensive three-dimensional maps of the universe ever assembled. Euclid will survey approximately 14,000 square degrees of sky, which is roughly a third of the entire celestial sphere. In doing so, it will obtain the positions and shapes of over 1 billion galaxies, some of them as far back as 10 billion years in cosmic history, which is to say at a time when the universe was roughly 3/4 of its current age. What Euclid is specifically designed to probe is the dark energy equation of state parameters. The same quantity that the DESI results have hinted is not exactly -1. Euclid aims to constrain that parameter with sub-percent precision. That level of precision matters because the difference between a cosmological constant at exactly -1 and a slowly evolving dark energy field at -0.95 or -1.05 is the difference between two entirely different pictures of the universe's future and its underlying physics. A constant needs no explanation for its dynamics. A field has dynamics, which means it has a history and a trajectory, and those open a door to entirely new physics. In March 2025, Euclid released its first data to the public, its Quick Data Release 1. In just 1 week of observations covering 63 square degrees of sky, the telescope had captured 26 million galaxies, the most distant of which are roughly 10.5 billion light-years away. The consortium of more than 2,600 scientists from over 300 laboratories had only completed a fraction of 1% of its planned observations at that point. But the data already offered a preview of the cosmic web in stunning detail. The shapes, sizes, and clustering properties of these galaxies contain encoded information about how dark energy has behaved over billions of years. Extracting that information from the full survey will take years of analysis, but the first data release confirmed that the instrument is performing as designed and that what comes next will be unprecedented in its scope. The full cosmological results from Euclid's primary mission are expected in 2026, and they will provide an independent test of the DESI findings. If Euclid's galaxy clustering and weak lensing measurements agree with DESI's preference for evolving dark energy, the case for new physics will become very difficult to dismiss. If they do not, the tension within the data will itself become something to explain. Either outcome advances understanding. Alongside Euclid, the James Webb Space Telescope, which began science operations in 2022, has been changing the way we see the early universe. Webb's contribution to dark energy is less direct than Euclid's, but it is no less important. The James Webb Space Telescope has verified the local measurements of the Hubble constant, confirming the supernova-based measurements that give a value of around 73 kilometers per second per megaparsec, rather than reducing the gap with the CMB-based value. That confirmation has made the Hubble tension harder to attribute to measurement error, and more likely to require a genuine theoretical resolution. Beyond the Hubble tension, Webb has been peering into the universe's earliest epoch, imaging galaxies that existed when the cosmos was only a few 100 million years old, far less than 1 billion years after the Big Bang. What it has found there has itself generated new tensions. Some of the early galaxies Webb has observed are larger, more massive, and more structurally complex than the standard cosmological model predicts they should be at that age. The standard model of galaxy formation, built on the lambda CDM framework that includes dark energy and cold dark matter, predicts that galaxies should grow gradually through the slow accretion of smaller structures over billions of years. But some of the early galaxies Webb sees appear to have assembled their stellar mass faster than the standard model allows. This is an active area of investigation, and the observations may find conventional explanations. But it is part of a broader pattern in which the better our instruments become, the more frequently the standard model is surprised. Consider what this pattern means in aggregate. The Hubble tension. The DESI hints at evolving dark energy. The unexpected early galaxies from Webb. The failure to detect dark matter particles after decades of underground searches. Each individual anomaly might be explained away. Together, they form a picture of a standard model under genuine stress, a framework that works extraordinarily well for most purposes, but that is increasingly encountering the edges of its domain of validity. Let's go deeper into what dark energy's presence means at the level of the vacuum itself, because this is the place where the physics becomes most confronting and most strange. Quantum field theory, the framework that underlies the standard model of particle physics, treats the vacuum not as empty space, but as a sea of fluctuating quantum fields. Every cubic centimeter of what we call empty space is, at the quantum level, churning with activity. Virtual particles appear and annihilate. Fields oscillate at their lowest possible energy states. The vacuum is, in quantum mechanical terms, never truly at rest. This is not a metaphor. The reality of vacuum fluctuations is confirmed by measurable physical effects. The Casimir effect, first predicted by physicist Hendrik Casimir in 1948, is one of the best known. Two uncharged metal plates placed in a vacuum will experience a small but measurable attractive force produced by the fact that the quantum field fluctuations between the plates are slightly suppressed compared to the fluctuations outside, creating a net pressure pushing the plates together. The vacuum pushes things. The vacuum has energy. This is established, measured, demonstrated physics. The problem is that quantum field theory does not merely predict that the vacuum has energy. It predicts that the vacuum has an enormous amount of energy, far more than the cosmological constant could account for, by a factor of between 50 and 120 orders of magnitude. The vacuum energy contribution from quantum electrodynamics alone, from the fluctuations of the electromagnetic field and the virtual electrons and positrons it produces, is predicted to be overwhelmingly larger than the observed dark energy density. Add in the contributions from the weak and strong nuclear forces, from the Higgs field, from all the quantum fields that make up the standard model of particle physics, and the predicted vacuum energy is incomparably larger than what we observe. In 1967, Soviet physicist Yakov Zeldovich made a key observation. Even if you set the classical cosmological constant to exactly 0, quantum theory won't let it stay there. Because every quantum field fluctuates in the vacuum, first principles quantum theory forces a non-zero vacuum energy back in regardless. This is the origin of what's now called the cosmological constant problem, a mismatch physicists have described as the largest discrepancy between theory and experiment in all of science, and probably the worst theoretical prediction in the history of physics. Each quantum field's vacuum fluctuations contribute its own share to the cosmological constant, and every single one of those contributions comes out orders of magnitude larger than what we actually observe. Here is one way to feel the weight of this. If you took a box of space 1 meter on each side and filled it with the vacuum energy that quantum field theory predicts, it would contain enough energy to outshine every star in the observable universe, multiplied by a factor so large it exceeds any number with a common name. The observed dark energy density of that same cubic meter of space is roughly the energy equivalent of a few hydrogen atoms. The gap between those two numbers, the predicted and the observed, is the cosmological constant problem. The most common response to this problem, among physicists who have spent careers trying to address it, is that something must be cancelling out almost all of the quantum vacuum energy, leaving only the tiny observed residue. Some mechanism of near-perfect cancellation must be at work, reducing the theoretical prediction by a factor of 10 to the 120 or so, and leaving the faint but non-zero remainder that drives the acceleration we measure. But no such mechanism is known. Supersymmetry, the the theoretical framework that pairs every particle with a heavier partner and promises cancellations between them, was the leading candidate for decades. It predicts that the contributions of bosons and fermions to the vacuum energy should cancel precisely, but the Large Hadron Collider at CERN, which began operating in 2008 and has searched extensively for supersymmetric partner particles, has not found them in the mass ranges where they would need to be to solve the cosmological constant problem. The supersymmetric partners are not there where the theory needs them, and without them, the cancellation mechanism does not work. String theory, the broader framework within which supersymmetry lives, offers a different response. Not a single cancellation mechanism, but a landscape, an enormous number of possible vacuum configurations, each with a different value of the cosmological constant. The string landscape might contain something on the order of 10 to the 500th power different possible vacua, each one a distinct configuration of the extra dimensions that string theory posits. In this picture, the cosmological constant is not a uniquely determined quantity, but one of an enormous number of possible values, and we find ourselves in a universe where the value is small because small values permit the existence of observers. This is, in its broad outline, the same anthropic argument Weinberg made in 1987, now embedded in a theoretical structure that at least offers a mechanism for how many different values might exist. But string theory has its own difficulties. It has not been confirmed by experiment. Its extra dimensions and its landscape of vacua have not been directly observed. It makes no specific predictions about which vacuum we should inhabit, only the anthropic constraint that it must permit observers. Many physicists find this deeply unsatisfying, and some argue that a theory that can accommodate almost any value of the cosmological constant is not really explaining the cosmological constant at all, but rather retreating from the goal of explanation. The cosmological constant problem is not a problem in the sense of an inconvenience waiting for a clever calculation to clear it up. It is a problem in the sense of a foundational incompatibility between the two most successful theoretical frameworks in the history of physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum field theory, which describes the behavior of particles and forces at the smallest scales, simply give incompatible answers to the question of what the vacuum contains. Bringing them into agreement requires something genuinely new, something that neither framework currently provides. And so, the cosmological constant problem sits at the center of fundamental physics, unresolved after more than 50 years of serious attention, connected to some of the deepest questions about the nature of space, time, and energy. It is not a lack of effort. The literature on the cosmological constant problem runs to tens of thousands of papers. Every conceivable approach has been explored, from modifications of gravity to new quantum field theories, to extra dimensions, to quantum cosmology, to thermodynamic arguments, to anthropic selection. None of them has produced a widely accepted resolution. What this means, in the context of dark energy and the accelerating universe, is that the 68% is not merely a number that sits unexplained in an otherwise satisfying theory. It is the surface of something deeper. The accelerating expansion is real. Its effects are measured with precision. Its cause is, at the level of fundamental physics, genuinely unknown. And the gap between the vacuum energy that quantum mechanics predicts and the vacuum energy that cosmology observes is perhaps the most dramatic demonstration in the entire history of science that our two best theories of the world are deeply, structurally incomplete. There is something worth dwelling on in that situation. Not despair exactly, not paralysis, but a genuine intellectual vertigo. Physics has been wrong before and has survived. Newton's mechanics, which worked with extraordinary accuracy for over 2 centuries, turned out to be an approximation of special relativity, itself an approximation of general relativity. The quantum mechanics of the early 20th century, which seemed baffling and counterintuitive, became the foundation of chemistry, materials, science, and electronics. Science has a long history of discovering that the framework it trusted was incomplete, and emerging from that discovery with a deeper framework that explained both the old successes and the new anomalies. The incompleteness is familiar. What is unusual here is its scale. The cosmological constant problem is not a small correction to an otherwise perfect theory. It is a factor of 10 to 120. It is not a subtle discrepancy at the margin, it is a chasm. The resolution, when it comes, will not be a minor adjustment. It will be something that changes how we understand what space is, what energy is, and what the vacuum contains. It will almost certainly change how we understand the future of the universe as well. And that future is written for now in the 68%. The quiet, relentless, inexplicable push that has been separating the galaxies for 5 billion years, that is separating them still as you read this, that will continue separating them long after every star has burned to nothing and every black hole has dissolved into the cold whisper of Hawking radiation, and that will keep pushing the void wider and emptier for timescales so vast that no number spoken aloud quite conveys them. That is what dark energy is. Not in the sense of a mechanism, or an explanation, or a theory, but as a fact about the world. It is the thing that fills space. It is the thing that outlasts everything else. It is the dominant term in the universe's energy budget, and it is, in the most literal sense, the force that is deciding where all of this ends. The tools we are building to understand dark energy are themselves worth pausing over, because they represent something remarkable about the moment in history we happen to occupy. We are the first generation of observers to know that the universe is accelerating. That knowledge is less than 30 years old. And we are now, in the span of a single human lifetime from that discovery, deploying instruments of a precision and scale that would have been inconceivable to the astronomers of 1998 who first found the signal. Let's consider what that means for how the picture might change. The Dark Energy Spectroscopic Instrument has been operating on the 4-meter Nicholas U. Mayle telescope at Kitt Peak National Observatory in Arizona, and it is not subtle in its ambition. Its fiber positioning system places 5,000 optical fibers onto the focal plane of the telescope simultaneously, each one directed at a different galaxy, each one collecting the spectrum of that galaxy's light in real time. In a single night of observing, DESI can measure the redshifts of more than 100,000 galaxies. In 3 years, it has built a 3-dimensional map of the universe across billions of light-years of cosmic history, tracing the baryon acoustic oscillation scale, that frozen fingerprint of early universe sound waves at multiple epochs and multiple distances. It is essentially reading the universe's expansion history as a continuous record rather than as a single snapshot. The fact that 3 years of DESI data have produced a 4.2 sigma preference for evolving dark energy, strengthened from the first year's hint, means the signal is persisting as the dataset grows. A statistical artifact would typically diminish as more data arrive, averaging out with more measurements. A real physical signal would remain and strengthen. The DESI result has done the latter. This does not make it a confirmed discovery. The threshold has not yet been crossed, but the direction of travel, from a moderate hint to a stronger and more consistent hint across multiple independent datasets combined with DESI, is the kind of trajectory that the cosmological community watches closely. What the DESI results specifically suggest, in the framework physicists use to parameterize dark energy evolution, is that dark energy may have been stronger in the recent cosmological past than it is today. The technical language for this uses 2 parameters: the present value of the equation of state, written W0, and its rate of change over cosmic time, written WA. For a true cosmological constant, W0 equals -1 and WA equals 0. The DESI data, when combined with measurements of the cosmic microwave background and type Ia supernova, prefer values where W0 is somewhat above -1 and WA is negative, meaning dark energy was somewhat more negative in its equation of state in the past, more strongly accelerating, and has been weakening toward the present. This is the thawing scenario, and if confirmed, it would mean dark energy is not a fixed background property of space, but a field with genuine dynamics, one that was frozen in a particular state and has been slowly relaxing. The implications of this, if true, go well beyond the observational cosmology community. A thawing dark energy field would have a future trajectory. It would continue to weaken. At some point, it might weaken enough that gravity reasserts itself over the cosmic expansion. The acceleration would stop. The universe might coast for an epoch, then slowly begin to decelerate. The distant future of isolation and emptiness, the heat-death scenario built on the assumption of a fixed cosmological constant, would have to be reconsidered. Not necessarily replaced by anything more comfortable, but revised. The timeline of the universe's future would look different. Some of the galaxies being carried toward the event horizon might, on a long enough timescale, come back into causal contact. This is speculative. The current data do not determine the trajectory of the dark energy field far enough into the future to say what it will ultimately do. Dark energy might thaw and weaken gradually, or it might thaw quickly and cross below the cosmological constant value into phantom territory, or it might stabilize. The observations constrain its behavior over the past several billion years. They say much less about the next several billion, and almost nothing about the deep future of 1 trillion years or more. The physics needed to project that far forward would require knowing the underlying theory of dark energy, which we do not have. There is another instrument that will contribute to this story. The Vera C. Rubin Observatory in Chile, built on Cerro Pachón at an altitude of 2,682 meters, finished commissioning its instruments in 2025 and has now begun its legacy survey of space and time, known as LSST, a 10-year survey of the southern sky. Over a decade of operations, the Rubin Observatory's LSST survey will photograph the entire southern sky every few nights, accumulating an archive of roughly 20 terabytes of imaging data per night, every night for 10 years. From that archive, astronomers expect to discover and characterize tens of millions of supernovae, trillions of individual astronomical objects, and the weak gravitational lensing signatures of billions of galaxies, all of which carry information about the large-scale structure of the universe and the dark energy that shapes it. The combination of DESI's spectroscopic redshifts, Euclid's weak lensing and galaxy clustering measurements, Rubin's photometric survey, and Webb's calibration of the distance ladder represents an observational attack on dark energy that is unprecedented in its breadth. These four instruments are measuring the same underlying physics through entirely different methods. If they converge, the result will be definitive. If they disagree, the disagreement itself will be informative. Either way, the next decade of cosmological observation is likely to be transformative in ways that the 1998 supernova papers were. But it is worth being honest about the limits of what observation alone can settle. Observations can determine whether dark energy is constant or evolving, and if evolving, how quickly and in what direction. They can tell us the value of the equation of state parameter with sub% precision. They can map the history of the universe's expansion with extraordinary accuracy. What they cannot do, on their own, is tell us why dark energy has the properties it has. The gap between the measured value of the cosmological constant and the quantum field theory prediction is not a gap that more precise measurements will close. It is a gap that requires theoretical understanding. And theoretical understanding, in this case, means a quantum theory of gravity, a framework that can calculate both the properties of space at the largest scales and the properties of the vacuum at the smallest, without getting an answer that is off by a factor of 10 to the 120. Let's talk about what that gap might actually mean, stripped of the technical language, felt at a more immediate level. Every cubic centimeter of the space between you and this screen contains dark energy. The room you are in contains it. The space between the Earth and the Moon contains it. The vast interstellar voids between galaxies contain it, and everywhere it is identical, the same energy density in every direction, at every point, filling all of it with the same quiet, unmeasurable push. Unlike matter, which clumps. Unlike radiation, which fades as the universe expands. Unlike dark matter, which follows gravity into halos and filaments. Dark energy is uniform. It does not clump. It does not dilute. It is the same everywhere, always, as far as any instrument has been able to determine. This uniformity is itself strange. In a universe where everything interesting happens because things are not uniform, because matter clumps into stars and galaxies, because temperatures differ between places, because structures form and evolve through the interplay of difference, dark energy is the great exception. It is featureless. It has no texture. It just is, the same everywhere, doing the same thing everywhere, driving the same expansion in every direction at every point. The universe's largest structure is its uniformity, and dark energy is the reason it persists. Think about what that actually means at a practical level. The dark energy in the space inside this room, in a volume of, say, 30 cubic meters, has a combined energy equivalent to something like 1/100th of a joule, a barely measurable flicker. You would need to add up the dark energy from a cube of space, roughly the size of a small country, to get the energy equivalent of a single gram of matter. It is unimaginably thin. And yet, scaled across the trillions of cubic light-years of the observable universe, it adds up to 68% of everything. The universe is so vast that even the thinnest possible energy density spread across it dominates its accounting. This thinness is part of why direct detection is impossible with any foreseeable technology. You cannot put a detector in a room and measure the dark energy in that room because the signal is so far below any threshold that can be reached. What you can do is measure dark energy's effects on the cosmic scale, where the integration over trillions of light-years of space makes the cumulative effect visible. The only laboratory large enough to detect dark energy is the universe itself. This is one of the most unusual features of dark energy as a scientific problem. Almost every other problem in fundamental physics can be addressed with laboratory experiments, particle accelerators, underground detectors, precision measurements of atomic transitions, or the like. Dark energy cannot. It does not interact with any detector at a strength that any current or foreseeable instrument could measure directly. We can only infer its existence from the universe-scale behavior of galaxies and the expansion of space. We are studying it the way a physician might study a disease entirely by watching its effects on the patient from across a room, without being able to take a sample, run a test, or examine the pathogen directly. This means that progress on understanding dark energy depends on increasingly large and precise observations of the universe as a whole, and on increasingly sophisticated theoretical frameworks that can make predictions about what those observations should reveal if a given theory is true. It is a slow, careful, patient kind of science, practiced on timescales of decades rather than years, with instruments that take a generation to plan, build, and operate. And it is being done. Right now, tonight, while the sky is dark over Kitt Peak and over Cerro Pachon, and above the cold quiet of the L2 Lagrange point where Euclid orbits, the instruments are collecting data. Galaxies a billion light-years away are leaving their faint traces in detectors. The universe is being measured. The 68% is being probed, one galaxy at a time, one spectrum at a time, one image at a time. There is something genuinely moving about that when you hold it alongside the strangeness of what is being studied. The thing that fills all of space and drives everything apart and cannot be detected in a room and has resisted every theoretical explanation for more than 50 years is being studied patiently and persistently by a few thousand people with instruments on 3 continents and in orbit, trying to read the universe's autobiography from the light of galaxies so distant that the light now arriving left them before the Earth existed. Step back even further from the specific instruments and the specific measurements, and consider the thread that runs through the entire history of this problem. In 1917, Einstein added the cosmological constant to his equations to make the universe static, because he assumed the universe was static. In 1929, Hubble showed it was expanding, and Einstein removed the constant. From the 1930s until the late 1990s, most physicists assumed the constant was 0. In 1987, Weinberg used anthropic reasoning to predict it should be small and non-zero. In 1998, Perlmutter, Rees, and Schmidt found exactly that, from measurements of exploding stars billions of light-years away. In 1967, Zeldovich had already pointed out that quantum field theory enforces a non-zero vacuum energy, and the cosmological constant problem has been unresolved since. In 2009, Planck launched to map the microwave background with unprecedented precision, confirming the 68% to better than 1%. In 2024, DESI hinted that the 68% might be changing, and now the instruments of the next generation are being aimed at precisely that question. It is 100 years of successive shocks, each one arriving just as the previous one was beginning to be absorbed. The universe is expanding. The expansion is accelerating. The thing causing the acceleration cannot be explained by the best theories physics has. The best theories physics has may need to be replaced to explain it. Each step leads not to a closed door, but to a deeper corridor. Something is worth dwelling on in the quality of this ignorance. It is not the ignorance of not having looked. We have looked with every instrument available. It is not the ignorance of carelessness. Some of the most careful, experimental and theoretical work in the history of physics has been aimed at this question. It is the ignorance of genuine confrontation with the limits of a framework. The framework works magnificently for almost everything it has been asked to do. It fails catastrophically at this one central question. That specific pattern of extraordinary success, punctuated by a single catastrophic failure, is, historically, the signature of a framework at the edge of its domain. Newton's mechanics worked magnificently for centuries. It failed catastrophically at speeds near the speed of light and at very strong gravitational fields. What replaced it was more fundamental and more comprehensive. The resolution of the cosmological constant problem, when it comes, is likely to be similar in character. Not a patch on existing theory, but something that re-explains both what we already knew and what currently defies explanation. We do not know when that resolution will come. We do not know whether it will arrive from a direction currently being explored, from string theory or loop quantum gravity or some modification of general relativity, or from a direction not yet imagined. What we know is that the question is real, the anomaly is real, and the data that are being collected right now are of a precision and diversity that will, at minimum, constrain the space of possible answers in ways that have never before been possible. The universe is expanding. It is accelerating. The reason is unknown. The direction is outward. The destination, across timescales that dwarf anything our intuition can reach, is toward an emptiness so complete that no record of what came before will survive. And everything we currently know, everything we have learned from every telescope ever built and every equation ever written, points toward that outcome without being able to tell us why the push exists, or whether it will last, or what it would mean if it ever stopped. That is where we stand. In a universe that is mostly dark energy, expanding faster every moment, with the instruments of a new generation watching, and the answer still ahead of us. Take stock of where we are. Dark energy fills 68% of everything. It has been pushing the universe apart for 5 billion years. It cannot be detected directly. It cannot be explained by the best theories we have. It drives the universe toward an ultimate isolation so complete that future civilizations will have no evidence it ever expanded at all. The instruments currently operating are producing hints, 4.2 sigma hints from DESI, that the 68% is not a fixed number, but a dynamic one, and the implications of that, if confirmed, will need a decade of further observation to settle. And the cosmological constant problem, the gap of 10 to the 120 between what quantum mechanics predicts and what cosmology observes, sits underneath all of it, unresolved and undiminished, the deepest single discrepancy between theory and measurement that physics has ever known. These threads run together into something that is difficult to name and impossible to look away from. It is, in part, a story about measurement, about what it means to build instruments patient enough and precise enough to ask questions that have never been asked before, and to sit with the answers those instruments return even when the answers are inconvenient. It is, in part, a story about theory, about what happens when the frameworks we use to understand the world encounter phenomena they were not built to describe, and what happens in the long interval between the failure of the old framework and the arrival of the new one. It is, in part, a story about time, about how the universe changes on timescales that dwarf human history, and about how the conditions that make science possible, that make this kind of patient watching possible, are not permanent features of the cosmos, but temporary ones, dependent on a particular configuration of matter and energy and the availability of light from distant sources. And it is, in part, a story about us, about the fact that we are here in this brief moment in cosmic history when the galaxies are still close enough to be seen, when the microwave background still carries its information, when the tools of observation and theory are finally sharp enough to reach the question of what dark energy is, even if they are not yet sharp enough to answer it. The question is available to us now. It may not remain available indefinitely. The universe that permits the question to be asked is not the universe that will persist forever. And the consciousness that asks it, that turns instruments toward the sky and reads the light of ancient supernovae and works the equations that describe the curvature of space, is itself a product of the conditions that dark energy is slowly, inexorably dismantling. One galaxy at a time, one receding light at a time, one horizon closing at a time. That awareness is something we will stay with in the pages ahead, not to resolve it because it cannot be resolved, but to sit with it fully, to let its weight settle, and to see what it actually means for the question of why any of this matters. What does it mean to live in a universe you cannot fully see, driven by a force you cannot explain, toward a destination you cannot prevent? That question has been building beneath everything we have traced tonight, and it deserves to be held directly now, without deflection, without the comfort of the next data release or the next theoretical proposal. Not because the science stops here, but because the science has carried us to a place where the implications exceed what science alone can process. Consider the situation plainly. We exist inside a universe that is 95% composed of things we cannot detect and do not understand. The 5% that is familiar to us, the atoms and molecules and light that make up every star, every planet, every living thing, every instrument ever built, is a trace ingredient in a cosmos dominated by dark matter and dark energy. The structure of everything we can see, every galaxy and cluster and filament in the cosmic web, was shaped by invisible scaffolding we have never touched. And the future of everything we can see is being decided by a force whose nature is genuinely, profoundly unknown. We are not ignorant of this. We are precisely ignorant of it. That is something different from ordinary not knowing. We know the shape of what we don't know. We know the number it produces. We know when the acceleration started 5 billion years ago, and we know what it is doing to the distribution of galaxies across the sky. We can calculate the future it produces, era by era, across timescales of trillions and quadrillions of years with reasonable confidence. What we cannot do is reach inside the vacuum and find the mechanism. We can describe the symptom with extraordinary precision. We cannot find the cause. What does it mean to be capable of that kind of precise ignorance? To build instruments of exquisite sensitivity that return again and again confirmation of something you cannot explain. To have the best theoretical frameworks in human history fail by a factor of 10 to the 120 to predict what every cubic centimeter of space contains. It means we are at one of those rare and unsettling moments when the map runs out. The road does not continue where the signs said it would. The framework that was the foundation of understanding has reached the edge of what it was built to describe, and the next framework has not yet arrived. This is not a comfortable place, but it is an honest one, and there is something in the honesty itself that deserves recognition. Because here is the thing most people don't realize about the history of this precise discomfort. Every time physics has found itself in this position, every time the framework hit its limits and the anomaly persisted and the theorists could not explain it, what eventually emerged was not just a patch on the old understanding, but something that expanded the conception of what the universe is. Newton's mechanics gave way to relativity, which showed that space and time were not the fixed background stage we assumed, but a dynamic fabric that bends and curves under the influence of matter and energy. Classical physics gave way to quantum mechanics, which showed that the behavior of matter at the smallest scales is irreducibly probabilistic, that particles do not have definite positions until they are measured, that the vacuum seethes with activity. Each revolution did not merely correct the old theory. It revealed that reality was stranger and more interesting than the previous framework could accommodate. The cosmological constant problem is the size of the gap that precedes a revolution of that order. Can we know, from inside this moment, what the revolution will look like? No. We cannot, and that is worth saying directly. The history of physics offers no guarantee that the next framework will be beautiful, or simple, or satisfying. It offers only the pattern that something has always come. Something that explained the anomaly, that unified what had seemed irreconcilable, that made the new view feel, in retrospect, more natural than the old one, even when it was initially more strange. We may never know what dark energy is. That possibility has to be faced honestly. If the resolution requires an observation that exceeds any possible instrument, or a theoretical insight that exceeds any mind, or an experiment that cannot be performed within the confines of a single universe, then we may reach the edge of what is knowable from where we stand. The honest scientific position includes that possibility. It does not insist on eventual resolution simply because resolution would be satisfying. What we can say is this: the question is real. The push is real. 68% is real. And right now, tonight, the instruments at Kitt Peak and in orbit and on Cerro Pachon are watching it, measuring it, pressing as close as they can to the thing that fills all of space and cannot be touched. Now, hold all of this at once. Hold the 1929 paper by Edwin Hubble, the discovery that the galaxies are receding, the moment when the universe stopped being a static stage and became something expanding, something with a history, something that was different in the past and will be different in the future. Hold the 1998 result, the supernovae fainter than expected, the two independent teams arriving at the same conclusion that nobody wanted to be true, that the expansion is not slowing, it is speeding up. Hold Fritz Zwicky in 1933, looking at the Coma cluster and finding that the galaxies were moving too fast for the visible matter to hold them, and being dismissed as too outrageous to believe for 40 years. Hold Vera Rubin in the 1970s, galaxy after galaxy, rotation curve after rotation curve, each one flat where the physics said it should fall, until the case for dark matter became impossible to ignore. Hold the Planck satellite, floating in the cold dark of space, mapping the microwave background at 1 part in 100,000, and returning a universe that is 68% dark energy, 27% dark matter, 5% everything familiar. Hold DESI, 5,000 fibers reading 5,000 galaxies simultaneously, building its three-dimensional map, finding its 4.2 sigma hint that the 68% might be moving. Hold the cosmological constant problem, 10 to the 120, the largest discrepancy between theory and observation in the history of physics. The vacuum that should roar, but instead whispers. Hold the timeline, 100 trillion years to the last stars, a Google years to the last black holes. And then the dark era, spreading outward forever, with no energy available for any process, no gradient to drive any reaction, the universe at maximum entropy and minimum temperature and zero complexity, a cold, dark fog of scattered particles drifting apart in an expanding void. Hold all of it and ask, what does it mean that we are here, now, in this specific moment of cosmic history, able to see the galaxies before they recede beyond the horizon, able to measure the microwave background before it redshifts further into the noise, able to detect the acceleration before its consequences become irreversible? We are not at the beginning of the universe. We are at a specific point in its middle age, 13.8 billion years after the Big Bang, roughly 5 billion years into the epoch of acceleration, with perhaps a few more billion years of comfortable stellar conditions remaining before the Sun enters its red giant phase, and the conditions for life on Earth change fundamentally. In the full arc of the universe's timeline, from its beginning to the dark era a Google years away, we are in an extraordinarily brief, extraordinarily particular moment. And in this moment, by a chain of events that is also extraordinarily particular, matter has organized itself into the shape of creatures who can look at the sky and build instruments and write equations and ask what is out there and why it behaves as it does. Creatures who can measure the acceleration of the universe and find it inexplicable. Creatures who can trace the timeline of the far future and feel something about it. What is that something exactly? Is it grief at the emptiness that is coming? Is it a wonder at the scale of what exists? Is it humility at the smallness of everything familiar in the face of the 95%? Is it something without a name, the feeling that arrives when you hold simultaneously the precision of the measurement and the depth of the mystery, the extraordinary competence of the instruments and the extraordinary incompetence of the theories? Here are questions that cannot be answered, but will not be quiet. What would it mean If dark energy is not a property of space, but a field with a memory, a trajectory, a destination, what would it mean if the cosmological constant problem is eventually solved, and the solution turns out to imply that the universe's future is nothing like the heat-death scenario? What would it mean if it is never solved? What would it mean if the DESI results solidify into a confirmed discovery, and the cosmological constant turns out not to be constant after all? What will the universe look like to whatever can still observe when the last star burns out? What will it be like when the last black hole dissolves? Is there a sense in which anything that ever happened, anything that was ever known, can persist in any form across the dark era? What is the relationship between the question-asking creatures who live in the stelliferous era and the absolute silence of the era that follows? Was there ever anything it was like to be the universe before it produced minds that could wonder about it? Those questions do not have answers. Not yet. Perhaps not ever. We cannot know what lies beyond the edge of the knowable, and the honest position is to say so without flinching. We may never know what dark energy is. We may never solve the cosmological constant problem. The revolution that closes the 10 to the 120 gap may not arrive in any human lifetime or any number of human lifetimes. The universe may continue expanding and accelerating forever without ever revealing the mechanism behind the push, carrying the galaxies apart, emptying the sky, dissolving the last structures, and proceeding into a silence so total and so permanent that the whole era of stars, the whole era of life, the whole era of question-asking will have left no trace that anything ever existed. That possibility is real. It has to be held. And yet, consider what it means that we are the part of the universe that is noticed, not God, not an outside observer, not something standing apart from the cosmos and watching it, something inside it, something made of the same atoms that were forged in stellar furnaces, the same quantum fields that fill the vacuum, the same matter that was drawn by dark matter halos into the gravitational wells where galaxies formed. We are continuous with all of it. We are not separate from the expanding universe. We are inside it, made of it, looking back at the thing we are part of. And in that regard, something extraordinary happens. The universe becomes aware of itself. Not fully, not perfectly, with the partial, uncertain, tool-using, error-making, perpetually revised awareness of a species that has been doing science for a few centuries at the scale of a cosmos that is billions of years old. But be aware, measurably, verifiably, genuinely aware of its own structure, its own history, its own future, its own mysteries. One generation traces the recession of the galaxies. One generation finds the acceleration. One generation maps the microwave background. One generation points DESI and Euclid at the sky and finds a 4.2 sigma hint that the constant is not constant. Each generation inherits what came before and extends it further. Each generation is brief, vanishingly brief against the timeline of the cosmos. And each generation, for the duration of its brief moment, is the universe looking at itself. That is not a small thing. It is not nothing. In a cosmos that is 95% dark, that is mostly made of things that neither emit nor absorb light, that is driving inexorably toward a condition of maximum entropy and zero complexity, the existence of any configuration that knows it exists is remarkable. The existence of a configuration that can measure the expansion rate, calculate the far future, feel something about the result, and try to understand the force behind it is extraordinary. We are small. The local group is small against the observable universe. The observable universe is small against what lies beyond the event horizon, which is, in turn, small against whatever larger structure might contain it if the multiverse is real. The stelliferous era is brief against the black hole era, which is brief against the dark era, which is brief against whatever lies beyond in the topology of a universe at maximum entropy. Everything we know is small. Everything we have measured is a thin slice of what exists. Every instrument we have built is a match held against the dark. And still, one equation at a time, one observation at a time, one carefully checked result at a time. The match is lit. The darkness is, for a moment, pushed back. The question is asked. The answer, partial and provisional and uncertain as it is, arrives. And in arriving, it changes what is possible to know, what is possible to ask next, what can be reached for in the following generation. That is not nothing. It is, in its way, everything. The universe is mostly dark energy. It has been pushing outward for 5 billion years. The 68% will keep pushing long after this planet is gone, long after the Milky Way has merged into Milkomeda and floated alone in an emptying void, long after the last star has cooled, long after the last black hole has exhaled its final quantum of Hawking radiation into the dark. The push does not care about the question askers. It does not know they exist. It will proceed regardless. But the question askers existed. They looked up. They measured. They built instruments of extraordinary delicacy and aimed them at an expansion they could not feel, and a force they could not touch, and a future they could not prevent. They sat with the mystery without resolving it, and kept working anyway, one paper at a time, one data release at a time, one sleepless night at an observatory at a time. And somewhere in the middle of all of it, on a night like this one, someone lay down in the dark and listened to the universe explain itself, as far as it has been explained, and felt the weight of the 68%, and the strangeness of the vacuum, and the long silence at the end of things, and was not crushed by it, was held by it instead. The way you are held by something vast and old and indifferent, that is also somehow the same thing you are made of. Sleep well tonight, knowing that the instruments are watching, the galaxies are still there, and the universe, for all its darkness, has arranged itself in at least one place into something that notices. Good night.